I forgot to record. We just talked about why it's helpful, necessary, and not helpful. Tell me in the chat, do you guys prefer to do A or do you prefer to do F? I have 2 answers. I'm going to wait for a couple more just to make sure you guys are all on the same page. Oh, you are not all on the same page, but most of you are. So we're going to do A. Oh, we have 2 Fs. We're going to do A. There are a whole bunch of A's. So A, I have y is equal x cubed all over to the 6. Okay, so this is what we're going to do now, and I'm going to remind us over here of our log rules on the side. We have log of AB is equal to log of A plus log of B. Log of A over B is equal to log A minus log B. And log of A to the B is equal to B ln A. Okay, we also had a little star. I'm going to do the most important one here, which is ln of e to the A is just equal to A. And none of these are derivatives. These are all just simplification rules. So what's my first step of logarithmic differentiation? We already identified that it was going to be helpful here. So how do I start?
You take ln of both sides.
I take ln of both sides. You got it. So I'm going to have ln y is equal to ln of all of this stuff. Good. Now, which one of those 3 rules can I use first? For my second step, which is to simplify.
The second one.
You got it, Kenna. I can separate my quotient. So here we're using rule 2. And we're separating that quotient. So I'm going to have ln of the top minus ln of the bottom. Now which rule can I use, or am I done simplifying?
You can use 3 for the power rules.
So can I use that immediately? So like, yeah, I've got a bunch of powers, but is everything inside to like different powers?
Yeah.
Yeah, so I can't start off by using that rule because I would need everything inside to be to the same power. So which rule do I need to use first so that I can eventually use 3?
Rule 1.
Rule 1, you got it. And how many things can I separate in my first ln?
3.
3, you got it. So I'm gonna have 1, 2, 3 things. And how many things can I separate in my second ln?
3 as well. No.
Also 3. 1, oops, come on, pen. 1, 2, 3. So we're gonna separate that using the product rule, the product one, number 1 up there. So we'll have ln y is equal to, and now we're using rule 1, ln of x cubed plus ln of 3x minus 6 to the 5th plus ln of e to the 2x squared plus 1 minus ln of 8 to the x, ln of x plus 1, ln of x plus 1, my bad. Ln of x plus 1, and then ln of 3x minus 7 to the 6. Okay, I left some blanks there. What sign should go in between those lns?
Minus.
Minus, because we're distributing that minus sign. You got it. So there's a minus, there's a minus. Good job. Okay, now notice I can use rule 3 because now I have just x to the power of 3. Each thing in the ln is to the same power. So here I'm still in step 2, only now I'm using rule 3 over here. And I'll have 3 ln x, oops, plus 5 ln of 3x minus 6. What does ln of e to the 2x squared plus 1 equal?
Just the exponent, so 2x to the square plus 1.
You got it. So that's my star. So I'm going to add a little star over there because I'm also using the star. So plus 2x squared plus 1 minus x ln 8 minus ln of ln x plus 1. There's nothing I can do on that one. And then minus 6 ln of 3x minus 7. So there I use my third rule. Is there any more simplification I can do in any of these logs? Can I simplify more? Yes, no, I have no clue.
We're still not at the step of turning them into derivatives, no? Or are we?
Well, that's what I'm asking. So should I start taking derivatives, or can I simplify more using those 3 rules up there?
No, you can start taking derivatives.
I can start taking derivatives because when I look inside of these lns, I no longer have products, I no longer have quotients, and I don't have anything to powers. So I really, at this point, can only move on to taking derivatives. So that's my third step here, to take the derivatives. And what is the derivative of ln y?
Y prime over Y.
You got it, y prime over y. So I'll have y prime over y is equal to, and now my derivative rule tells me, so this is my simplified form. I just want to make that clear. This is the simplified form. I haven't taken any derivatives yet. Now I'm doing g prime over g for my logs. So this is 3 over x plus 5 times 3 over 3x minus 6 plus 4x plus 0. What's the derivative of x ln 8? This is one that we had like the little star in our.
Ln 8.
Say again?
Ln 8.
Just ln 8, you got it. So this is one that we said shows up a lot, so you need to be comfortable with it. Minus ln 8 minus 1 over ln of x plus 1 times 1 over x plus 1. Minus 6 times 3 over 3x minus 7. So are there any questions about this derivative right here? Is it okay? Okay, so in that case, my fourth step is to multiply y over, but when I multiply y over, what do I put instead of y?
The original equation.
The original equation, you got it. So I'm gonna have y prime is equal to the original equation, which is x cubed, 3x minus 6 to the 5th, e to the 2x squared plus 1, over 8 to the x, ln of x plus 1, 3x minus 7 to the 6. Good. Times that derivative that we just took there, plus 15 over 3x minus 6 plus 4x minus ln 8, minus 1 over x plus 1 ln of x plus 1 minus 18 over 3x minus 7. And that is my final answer. Are there any questions about what we just did here? Okay.
Yeah, I don't get how you got that derivative. The one that you like showed just before.
Okay, hang on. I'm going to go off to the side and do it then. So we have the derivative. Is this the one you're talking about, Alex?
Yeah.
Okay. So what I have here is I have my inside function. That's like my g. And remember we said ln of g prime is equal to g prime over g, which is technically the same thing as 1 over g times g prime. So far, so good?
Mm-hmm.
Okay, so my inside function, my g in this case, is ln of x plus 1. So I'm doing like 1 over ln of x plus 1 times the derivative of ln of x plus 1.
Oh, okay. I thought
Right.
it was where is it? The ln of ln x.
So it's actually really similar, and ln of ln x comes from the same thing. So like if we think about where ln of ln x comes from, it's the same thing. It's like we're saying 1 over ln x times ln x prime, which becomes the same thing. So then it becomes that, which is 1 over x ln x. So in the same way, this is actually the exact same form. It's like 1 over x ln x, but we have x plus 1 instead of x.
Oh, okay.
Yeah. Does that make sense?
Mm-hmm.
Cool. Any other questions about this problem? Okay, if you guys need to write, I'm going to come back down in just a second. But like I said, I want to do one of the ones where it's necessary. So B or D, I'm going to let you guys pick. In the chat, tell me privately, B or D. Okay, so I've got a lot of both here, but I think I have more D's at this point. So we're going to go with D, which honestly I think is maybe a better question in any case. B kind of looks scarier, and it maybe is, but I think that D has things in it that people tend to mess up more. So sine squared x plus 2 to the tangent x. Do you guys need a second, or can we move on? Okay, so here we said I've got x is down here and x is up here, which is why we definitely have to use logarithmic differentiation in this case. And my first step of logarithmic differentiation, we know, is to take ln of both sides. Now, when I'm simplifying, can I bring that tangent down immediately? Can I take that tangent and bring it to the front?
No.
Why not?
Yes.
Couldn't you bring like the 2 from the sign out? to
Okay,
make it-
so we are going to do that. But actually, and I'll do that right here. When I know that that sine squared is the same thing as sine x squared. But then all of that is still to the power of tangent x. So I can rewrite the sign like that, and that's actually a good plan. But what I see here is still that even everything inside is to the power of tangent. which means that I can start by bringing the tangent to the front. Does that make sense? Good, okay. So then I have ln y is equal to, I'm using my third rule here because I'm bringing my power down, to get tangent x times ln of sine x squared plus 2. Now question, can I bring that 2 down to the front? Can I say 2 ln of sine x plus 2? What do you guys think? Good job. So yeah, the answer is no. The answer is no because of this plus 2 right here. So that plus inside stops me from being able to do any more simplification, which is why in those other questions we had up there where we had all those pluses, logarithmic differentiation wasn't helpful. When we have pluses, we can't do anything. So the plus 2 stops me from being able to do more simplification. So that brings us to our step 3 immediately, where remember, we're doing logarithmic differentiation because we have to, so we have a product rule. And I'll have y prime over y. What's the derivative of tangent?
Cotangent?
No,
Isn't it the secant squared?
secant squared. So I have secant squared x, the derivative of the first, times the second, plus the first, times the derivative of the second. So the derivative of the second, that's now my log rule, where this thing inside is my g. So I'm going to have a sine x squared plus 2 on the bottom, and then a sine x squared plus 2 prime on the top. So when I do that top, I'm also going to bring my y over. So now I'll have y prime is equal to sine squared x plus 2 to the power of tangent x. Remember, that's our y. We don't write y. We write the original function times secant squared x ln of sine squared x plus 2 plus tangent x. What's the derivative of sine squared x? Tell me in the chat, what's the derivative of sine squared x? Yes, Luca. So no, 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 yes, yes, no. So this actually is one of the things that you guys really were challenged with. It seemed difficult for you in the group work, the last group work that we did. I've corrected your group work. I also posted the solutions and a link to the video where I talk about those solutions. I really highly recommend that you watch that video. It's like 10 minutes long. Click the link, go watch the explanations, and it will help you with this type of thing. I talk in depth about this a little bit. So if I'm doing the derivative of sine x squared, I have to remember that what's going on here is it's like I have a g squared. So that's 2g, g prime, where my g is sine x. So I bring the 2 down, I don't touch what's inside, and then I pull out the derivative of sine. So what I end up with is 2 sine x cosine x, which actually David, is technically the same thing as what you wrote. So what I should have on top here is 2 sine x cosine x. And then I close my parentheses, and this is my final answer. Okay, are there any questions about this problem or about logarithmic differentiation in general before we move on to our next topic? No questions? Then we are moving on. Hello, Cam. To higher order derivatives. Which is really bringing us into the last section of the class, because we're no longer learning techniques to take derivatives. We're now learning about derivatives and what we can do with derivatives. So we've kind of moved into the application section of the class, and this leads us into that. Okay, no last minute questions about logarithmic differentiation? We're all ready to move on? All right then. So higher order derivatives. So derivatives are functions, right? And they are functions of other functions. So if I have a function, I can take its derivative. But because derivatives are also functions, that means I can take the derivative of the derivative. And then I can take the derivative of that. And then I can take the derivative of that. So higher order derivatives are taking derivatives of derivatives. And it's actually pretty much as straightforward as that. That said, we're going to start off with some notation and some vocabulary. So if I have a function, f of x, and I take the derivative of it, we write f prime of x, or we write dy dx. I haven't been using the dy dx notation a lot, but they're both very useful. So this is the derivative of f, and it's what we call a first derivative because it's just one derivative. So this is the first derivative of f of x. If I take the derivative of that derivative, then what I end up with is f double prime of x, where we just write 2 primes. Over here, I write d2y dx2. So I put a little 2 between the d and the y, and then a 2 after the x. And this is my second derivative of f of x. But because the derivative is a function, and therefore the second derivative is also a function, I can take the derivative of that as well and get the third derivative, which would be f triple prime of x, or d3y dx3. This is my third derivative. long do you think I can do this? How many derivatives do you think there are? I have a first, a second, a third.
Infinite.
Infinite. I can keep going forever
Forever.
and ever and ever. So that said, if I keep going forever and ever and ever, if we look at this left-hand notation where I just write a little prime, let's say that I have like the 8,000th derivative. It doesn't really make sense to write 8,000 primes. 8,000 little dashes would be a little bit insane. So at the fourth derivative, instead of doing primes, I write 4 in parentheses. So I'll have the fourth derivative would be f4 of x, and it's not just to the power of 4. Those parentheses are important because they tell you it's a derivative, not a power. This other notation, my Leibniz notation, doesn't change. Okay, so what that means is the fifth derivative, the sixth derivative, I can keep using this notation forever. So I also might want, for example, the nth derivative of x. So this is, I mean, of f of x. This is the nth derivative of f of x. So this is just vocabulary and notation. Okay, so the main thing that you need to know about taking higher order derivatives is that your life is going to be a lot easier if you simplify every time you take a derivative. Sometimes your life will even be easier if you simplify before you start taking derivatives. So the main thing about higher order derivatives is simplification is key. So with that in mind, let's take some. Okay, so I want to calculate the third derivative of f of x is equal to 2x plus 3 times x squared plus 2. So in this form right here, does this require a product rule?
Yep.
Yes. Could I avoid a product rule by expanding this?
Yeah.
Yes. So I don't have to do this, but expanding this first will allow me to avoid a product rule and thus make every consecutive derivative easier. Okay, so when I expand this, I can say that f of x is equal to 2x plus 3 times x squared plus 2, which is equal to 2x cubed first, plus 4x outer, plus 3x squared inner, plus 6 last, which I'm going to rewrite in descending order. Did expanding that give me a derivative that's incredibly super easy to take? Just simple power rules.
Yeah.
Good. So now when I do my first derivative, I get 6x plus 6 plus, 6x squared plus 6x plus 4. Is the derivative of that also really easy to take? Yes. So then my second derivative would be taking the derivative of that thing right there, and I would just get 12x plus 6. So then what's my third derivative equal?
12.
You got it. Okay. Yes.
Since we know there's going to be 3 derivatives, on the first step, we have only 1 to the power of 3, like 1 value to the third power. So we know that's the only one that's going to be last. So can we just eliminate everything else from the first step?
Yes. And that actually brings me to a little theorem that we're going to have right now. So what David just asked is actually a really important question because it leads us to the theorem. So I have 2x cubed plus 3x squared plus 4x plus 6. And what I was looking for was the third derivative. Did that 3x squared become 0 by the time I got to the third derivative? Yes. Did the 4x become 0? Yes. Did the 6 become 0? Yes. If I had taken one more derivative, what would the answer have been?
0.
0. So basically, what we're seeing here is that when we have a polynomial, the derivative of that polynomial will eventually become 0. Okay? When will that happen? The cubed became 0 at what power? So that 2x cubed, when would the derivative of it have become 0? At what, not what power, at what derivative?
Yeah, fourth.
The fourth derivative. When did this 3x squared become 0? The first it was 6x, then it was 6 with the second derivative. At the third derivative, the 3x squared became 0. So what we can see that we can use the power of a polynomial to determine at which derivative it will become 0. So we're going to have this as a little theorem here, and it helps us to take high derivatives of polynomials. So our theorem, and we're going to have to learn some vocabulary or remember some vocabulary to understand this theorem. So if f of x is a degree in polynomial, then f n plus 1 of x, in other words, the n plus 1th derivative will be 0. And Thus, every derivative after will be 0. Okay, so to understand this, there are two words that are kind of really important here: degree in and polynomial. What's a polynomial? Is x to the 1/2 plus 2 a polynomial? What do you guys think? Yes, no?
Yes.
So I'm getting a lot of
Yes.
yeses. The answer is actually no. The
Oh.
reason that the answer is no here is because that power is 1/2 and it is not a whole number. So a polynomial is when x is to the power of positive whole numbers. So x to the power of positive whole numbers. Which means technically that it can include constants. So that +6 there is a constant that counts as a polynomial. So we just said x to the 1/2 plus 2 is not a polynomial. Is this a polynomial? Is
No.
x to the -3? What?
No, it's not.
No, because that power is negative. So this is also not a polynomial. Is x to the 8th plus 9x to the 4th plus 6x squared plus 1 a polynomial? Yes, this is a polynomial. Is 8 a polynomial?
No.
Yes.
So over here in our definition, we said x to the power of positive whole numbers, and it includes constants. Turns out that yes, while 8 is a constant, it's also a polynomial. I can think of this as x to the power of 0, and that 0 is okay. So yes, this is, it might be weird, but this is a polynomial. Now the degree is the second thing that we have to talk about. The degree of a polynomial is the highest power of that polynomial. Okay, so what is the degree of x to the 8 plus 9x to the 4th plus 6x squared plus 1? What's the highest power there?
X to the 8th.
X to the 8. So the degree of this polynomial is 8. So this theorem tells me that by the 9th derivative, it will be 0. What is the degree of 8?
0.
You got it. That's a degree 0 polynomial. What's the degree of the polynomial that we dealt with up here?
Three.
You got it. The degree is 3. So by the 4th derivative, it would have become 0. So let's do just one quick example of this, and then we're going to look at other things where it doesn't work out quite so nicely. So I have 29x to the 31 plus 13x to the 12 plus minus 8x plus 1. So what's the answer? You got it, Cam. What's the degree of this? Well, first of all, is this a polynomial?
Yes.
Yes. What's its degree?
31.
You got it. So it's a polynomial of degree 31. So what that means is by the time we get to 31 plus 1, that's 32, the 32nd derivative, it should be 0. So the 32nd derivative is just 0 by the theorem. What about the 84th derivative?
That would just be 0.
It would also just be 0. Because the derivative of 0 is 0. So it's going to be 0 forever after that. Okay. Are there any questions about this theorem / what a polynomial is, what the degree of a polynomial is? Okay then. So this is really useful when we have polynomials, but unfortunately a lot of times we don't. And a lot of times we might have to like do some simplification. Like we had to multiply that thing out. We had to expand it to see that it was a polynomial. So when can we not use this theorem? So let's, and we have to go to our note that we made earlier about simplification. So find, evaluate the second derivative of f of x Okay. So if I do this as is right now, what rule will I have to use?
Product.
So this is a product rule. If I expand this in the same way I expanded the last one, can I avoid the product rule?
Yes.
Let's expand. Let's just check. So if I expand, I'm distributing that e to the x squared. So I'll have x cubed e to the x squared plus x e to the x squared.
We have 2 products right now.
Now I have 2 product rules. So in this case, does it make sense to expand or to just do the product rule?
Just do the product rule.
Just do the product rule, because expanding results in 2 product rules. So I'm going to do my product rule here. So f prime of x is, what's the derivative of e to the x squared?
X squared. Oh no, sorry, e to the x squared. Sorry.
This is my f. This is my g. What's the derivative of my f here? Actually, I'll just write it in parentheses. Then we'll have 3x squared plus 1. What's the derivative of e to the x squared?
2x times e to the x squared.
You got it. So this is a chain rule where I have like a g there. So the derivative of x squared is 2x, so this becomes 2x e to the x squared times x cubed plus x plus e to the x squared times 3x squared plus 1. Now my goal, we said, before I take the second derivative, I want to simplify this. My goal in life being to make this the simplest derivative possible. So we already saw in the first step that expanding was not a good plan. In the same way, when we have an e involved, we want to simplify kind of how we did before, but instead of finding the greatest common factor, the thing that makes the most sense is to separate the e from the polynomial, like we have it started to begin with, so that we just have one product rule to do. So when there's an e involved, don't factor out the greatest common factor, just factor out the e. And that way you can find something that results in just one product rule where you have the e part times a polynomial. So we're going to do that in this case. We're just going to factor out the e and see how we can turn this into the simplest derivative possible. So my f prime of x then will be, when I factor out e to the x squared, what's left over in my first term?
2x times x cubed plus x.
You got it, 2x times x cubed plus x. And what's left over in my second term?
3x squared plus 1.
Good. Inside of those parentheses, do you have a product rule? Is this a product rule here? I
Yeah.
just underlined it. It's not showing up. There we go. Is that a product rule here? Can I avoid that product rule by expanding?
Yes.
Yes. So here, expand to avoid product rule. So each time we're kind of saying, look, it's only polynomial stuff, so expansion makes sense. But when it was e, the expansion didn't make sense. So here I have e to the x squared times 2x to the fourth plus 2x squared plus 3x squared plus 1. So I have 2x to the fourth plus 5x squared plus 1. Now, is the result a simpler derivative than what it was before I started, before I simplified? Now I have one product rule. Before, I had two product rules, and one of those product rules was a product of 3 different things. The result, the simplified form, the derivative is much simpler. So now I'll have f prime of x is equal to, I'm just doing my one product rule, fg. 2x e to the x squared, we already found that, times 2x to the fourth plus 5x squared plus 1, plus e to the x squared times 8x cubed plus 10x. And that's my final answer. But if I needed another derivative, or if I'm asked for this final answer simplified, I would simplify again. And how would I simplify? In the same way that I simplified that first time around, by factoring out an e to the x squared. So I'd get that this is e to the x squared, 2x, 2x to the 4th plus 5x squared plus 1, plus 8x cubed plus 10x. That I would then expand and combine like terms to avoid another product rule. And now I'll combine my like terms to get e to the x squared, 4x to the 5th, plus 18x cubed, plus 12x. And so this is my final answer, and this is my simplified final answer. Okay. Are there any questions about what I've done here, the questions I've asked myself about how to simplify, things like that?
I have a question, but
Yeah.
not really about that.
Okay.
I don't know if I'm confusing this with something else, but I always thought a polynomial had to be 4 different like terms, I guess.
No.
I don't know what I'm confusing that with, because I know there's like binomial and trinomial.
So a trinomial would have
I-
like 3 different terms. A polynomial, so binomials and trinomials are types of polynomials,
Oh, okay.
right? So polynomial is kind of a general term that encompasses everything. I don't know what you could be thinking of that has to have 4 terms though.
I don't know. I remember there was something, but I don't remember.
But
the
in
name
any
of
case,
it.
a polynomial can have, it can be a binomial, it can be a trinomial, it can have however many terms you need, or you want, or it does. So it can have 1, it could have 7. Okay, so any questions about, does that clarify things for you, Alex?
Yeah.
I'm sorry, I don't know what you're
I
talking about with
understood
4
it before.
terms.
No. Yeah, I just figured that I'd maybe ask it because I just wanted to know what it was. I was confusing, but I couldn't like put my finger on it.
Okay, so let's look at another example. We're also going to find the second derivative. Find the second derivative of f of x is equal to 2x to the 7 plus 3 times the 5th root of x plus 6 over the square root of x. Okay, so after we do this question, I'm going to kind of write down like some strategy, like the types of things that are going through our heads. But in the last 2 questions, we were asking ourselves, can I avoid a product rule? Does expanding avoid my product rule? And in the first one, the answer was yes, so we expanded. In the second one, the answer was no, so we didn't, because we saw that expanding would actually add a product rule. Right now, when I look at this, what I have is a quotient rule. Can I avoid a quotient rule? I can. And this is a thing you're going to do when you have one term, when you have one term on the bottom. So one term in the denominator, we can kind of distribute it to each of the terms in the numerator. So in other words, what I have here is I'm going to start off by simplifying like this, 2x to the 7 over x to the 1/2 plus 3, the fifth root of x. What's that x to the power of?
1/5.
Good. So hopefully you guys remember that rule, x to the 1/5 over x to the 1/2 plus 6 over x to the 1/2. And I'm simplifying this in the same way that we simplified derivatives before when we were doing derivatives, to just have a power rule. So here I'll have 2x to the 13/2 plus 3x to the -3/10. And then plus 6x to the -1/2. So simplifying in this way, do I still have a quotient rule anywhere, or do I just have a simple power rule?
Well, miss. Couldn't you have just brought the root x up and made it like x to the -1/2?
Ultimately, it becomes the exact same thing if you do that. So like, I'm gonna write it like this. Like you would have 2x to the 7 plus 3x to the 1/5 plus 6 times x to the -1/2 that you're then distributing to the inside. And so ultimately, it's exactly the same thing.
Okay.
Yeah.
All right, thank you.
Yeah, because notice like each one of them got that x to the -1/2. Okay, so simplifying in this way allowed us to turn a quotient rule into 3 simple power rules. And power rules are the most powerful thing you have for higher order derivatives. And power rules, like I said, we love power rules. Power rules are the best for higher order derivatives, because that once you have a power rule, you pretty much only have a power rule. So f prime of x is 2 times 13/2, so that's 13x to the 11/2 minus 9/10 x to the -13/10 minus 6/2, so that's minus 3, x to the -3/2. So when I take my second derivative, since I turned it into simple power rules the first time, do I still only have power rules to do? If I want my second derivative, I've still just got simple power rules. I bring the thing down and I subtract 1. So f double prime of x is 13 times 11, that's 143 over 2, x to the 9/2, plus 90 plus 27, that's 117, over 100, x to the negative 23 over 10, and then plus 9 over 2, x to the negative 5 over 2. And that's my final answer.
Miss, shouldn't it be 26x 11 over 2? Because it was a 2x.
26x 11 over.
Because above it was 2x to the power of 13 over 2. So shouldn't they be 2 times 13?
But it's 2 times 13 over 2. So like when I bring the 13 over 2 down, I'm multiplying it by 2.
Got it.
And 2 times 13 over 2 is just 13. Okay, so here what we have is power rules are awesome because when you have a power rule, it's easy to just keep doing a power rule forever. So simplifying for higher order derivatives, we're trying to factor, expand, combine like terms, do what we have to do to get the minimum number of product rules and quotient rules. And the maximum number of power rules. I have 2 questions left I want to do today. I don't think I'm going to get to both of them. We're going to try. So this brings us to our next question where we're going to find the third derivative. So third derivative of ln of x cubed minus 1. There is literally nothing I can do to simplify that. My log rules will not happily simplify that because of that minus inside. We can't use the log rules. So what that means is we're just going to take the derivative as it is. F prime of x is equal to 3x squared over x cubed minus 1. Can I do the same thing I did in the last question to avoid the quotient rule here? Can I?
I think you could, but it wouldn't be.
I mean, so like think about how we avoided the quotient rule here. So Cam asked if we could do it a different way. And the reason that I didn't originally do it that different way is because it kind of helps us to see when we can't do that. Here, I was able to take that x to the 1/2 and distribute it to the 3 different things in the numerator. How many different things do I have in the numerator?
1.
1. So is it already kind of separated in that way? So the answer here is I really can't simplify this. I could turn the quotient rule into a product rule where part of it had a chain rule, but that's just going to make our lives even more challenging. So can't simplify to avoid our quotient rule. So we're just going to immediately take the derivative again and do that quotient rule. Where that's my f, and that's my g. So f double prime of x is the derivative of the top, which is 6x, times the bottom, minus the top, times the derivative of the bottom, divided by the bottom squared. Now, can I simplify this? So I really have two options here. I can just like expand and combine like terms, but I'm going to find the greatest common factor because that's one of the things that we've talked about a lot in this class is factoring out the greatest common factor. So what is the greatest common factor of the numerator? What happens on both sides of that minus sign?
3x?
Just 3x, you got it. My greatest common factor is 3x. So again, this is maybe not even the best way to approach this problem, but it might be the way that you think of since that's what we've done for simplification in the past. So when I factor out 3x, I have 2 times x cubed minus 1 minus x times 3x squared over x cubed minus 1 which gives me 3x times 2x cubed minus 2 minus 3x cubed over x cubed minus 1, which gives me 3x times minus x cubed minus 2. So based on what we said before, simplifying for higher order derivatives is largely trying to get rid of product rules and quotient rules. Is there anything I can do that would make this easier? Because I forgot my power of 2. Thank you, Kiana. Is there anything I can do at this point that might help me get rid of a product rule or quotient rule?
You can multiply the numerator with like the minus x cubed minus 2.
Exactly. So I can distribute that and get rid of a product rule, which we know is our ultimate goal with this thing. When finding horizontal tangent lines, like we were doing in the past, this is the better form. But for a higher order derivative, expanding that numerator gets rid of a product rule. So this form right here, negative 3x to the 4th minus 6x over x cubed minus 1 squared is definitely the better form for taking another derivative. So I stress, the good form for taking another derivative is not necessarily the same thing as the good form for finding a horizontal tangent line. We're really trying to minimize product rules and quotient rules here. So now we want our third derivative. F triple prime of x, I do the derivative of the top, negative 12x cubed minus 6 times the bottom minus the top times the derivative of the bottom, which is a chain rule. All divided by the bottom squared. And that is my final answer. We were not asked to simplify the third derivative, we just needed to get there. Okay. Are there any questions about the different thoughts that go into the simplification of these things in terms of minimizing those product rules and quotient rules? Okay, I'm gonna do one last question and I'm just gonna do it. I'm not gonna talk about it a lot. Next class, at the beginning of the class, we can talk about it if we need to, but really, I just kind of wanna show you guys some trig. I wanna have trig out there. So I'm just going to do this, and I want you to do your best to follow along as much as you can. Are there any questions before I do it? And this time we're only going to find the second derivative. So we're finding the second derivative of cotangent of x cubed. What's the derivative of cotangent?
Minus cosecant squared.
You got it. So this is minus cosecant squared of x cubed. We're doing a chain rule here, so I need to multiply by 3x squared. Now, one of the main reasons I want to talk about this problem really quickly, can I multiply that x cubed by that 3x squared?
No,
No.
because it's
You got it. It's cosecant squared of x cubed times 3x squared. It actually makes more sense to move that 3x squared to the front. And because I'm taking another derivative, I'm going to move that power of 2 to the end. Which means that now I have a product rule, and inside of that product rule, I have a chain rule. So f double prime of x is the derivative of the first times the second plus the first. And this is where it's going to be a little bit challenging, but I'm just going to do this, times the derivative of the second. So that's 2 cosecant of x cubed. What's the derivative of cosecant?
minus cosecant times cotangent.
So it's minus cosecant of x cubed times cotangent of x cubed times 3x squared. So that was like a double embedded chain rule. Here what I had was cosecant of x cubed to the power of 2. So it's kind of like I had a g squared. So I have 2g. That's my 2 times cosecant of x cubed times g prime. Now, if I want to simplify this, that 3x squared, negative 3x squared there, can be multiplied by the 2, can be multiplied by the 3 squared, and these negatives here can become plus. So I have plus 12 cosecant squared of x cubed times cotangent of x cubed.
You forgot your x to the fourth power.
Thank you.
It's 12x to the fourth power.
Now, question. What should I factor out to take the, I'm not asking you to take the third derivative, but if I were, what would be the best thing to factor out to make the third derivative as easy as possible?
6x
No,
cosecant squared x cubed.
just cosecant squared of x cubed. So what would be the thing to factor out? And the answer here is really similar to what we did with the e when we separated the thing into e plus polynomial. Or I'm sorry, e times polynomial. So the answer is cosecant squared of x cubed. And I want you guys, I'm going to write it here and I'm going to factor it out. I want you guys to look at that in your own time and think about why that's the best thing to factor out. And I want you to take away from this that trig high derivatives can get disgusting. We are done.